Welcome to our very first video lesson of the new year of 2021. So sorry you missed class, but I'm happy if you're just coming back to review what we did. So to start things off, we had a bit of a warm-up. I know that it's been a week and a half since we've had class, so I wanted to try and help dust out some of those cobwebs. So I made this all multiple choice. So the first question is, which of the following best describes molecular polarity? So this is what we were working on before winter break. So the first option was the temperature of molecules. That is not correct. We've not been working with temperature at all. I threw that in there because you might think, North Pole, South Pole are really cold, so maybe this has to do with temperature. Nothing to do with temperature. Next was the alignment, north and south of the molecule sides. Well, you might have been kind of tempted to choose this one because magnets have north and south, and it is all about magnetic attraction, negatives and positives. But when we talk about molecules, we don't talk about north and south poles. We just have positive and negative centers of charge. So it is kind of like a magnet, but that's still not a very good answer. And my molecules don't really align themselves north and south. Next was the strength of bonds between atoms. This was another one that might have been a little bit hard to figure if that was the right or the wrong answer. We did talk about how in a bond, the electrons kind of play tug of war. So that's still not quite the same as the strength of a bond because two elements might hold on stronger than two other elements. And that doesn't really have anything to do with how they're sharing those electrons. So this was kind of another misleader because you might think of the bond polarity being strong or weak. D was the best answer. Molecular polarity looks at how electrons are being shared around the whole molecule. So are the electrons hanging out more on this side than that side, or are they being shared equally around the entire molecule? So molecular polarity is all about how my electrons are being shared. Because if they're not being shared equally around my molecule, then I've got two poles, a negative and a positive pole. Negative pole where all my electrons are hanging out, and a slightly positive pole where my electrons are not hanging out. Next, I asked you to identify at least one shape that will always be polar. So remember, we had 6 different shapes, and I listed them all for you in the warm-up. 3 of these cannot make a non-polar shape. So my bent 120, my trigonal pyramidal, and my bent 109.5 all have lone pairs. And remember, a lone pair automatically makes your shape polar. The only time that's an exception is if you have all the same elements. So like O3 or N2 or Cl2. So if it's more than one element in your compound, and that's typically what we give you, if there's a lone pair on that central atom, it's going to be a polar shape. Your homework due on Thursday or Friday is to finish that molecular polarity gizmo that we started in class. So after the warm-up, I wanted to jump backwards a little bit and go over our notes again because it's been a week and a half. And then we started working on the molecular polarity gizmo in class. So remember, we're on our Unit 4 notes, Part 3. So you should go to your Google Drive. It should be there somewhere, your copy. If you're not sure where, you can type into that search bar, Honors Chemistry, Unit 4 Notes, Part 3. Or if you've taken my advice and create a chemistry folder, you should be able to find it very easily there. So you went back all the way to slide 10. So again, these are not new notes. This is just what we went over again in class. So when we're determining what shape the molecule takes, we're counting the number of domains. And domains are how many things are hanging off my central atom. You can either have lone pair electrons, so dots of electrons, or you can have atoms hanging off. So the two types of domains are those lone pairs and bonded pairs. So bonded domains or lone pair domains. Then we went over the practice again that we did earlier. So my first example here, I've got CH2F2. I have 4 things total around my central carbon, and those 4 different domains each have an atom in them. They have a bond. So I've got 4 bonded domains and no lone pair domains. Here we did SO2. I have 1, 2, 3 things hanging off my sulfur in the middle. 2 of those domains have bonded electrons, so that's 2 domains of bonded pairs. And then I've got 1 domain that just has 2 dots. That would be my lone pair. Then here I've got water. I have 4 domains total hanging off of my oxygen. 2 of those domains have bonded pairs, have hydrogens hanging off. And 2 of those domains have lone pairs, so I've got 2 and 2. Once you can count your domains and your type of domains, then you can figure out the shape. So counting the different types of domains helps you figure out the shape based on the graphic organizer in your notes. So if you have 2 domains with bonded pairs and no domains with lone pairs, you're linear. If you have 2 domains with bonded electrons and 1 lone pair, you're bent 120. Now, we didn't take time to go over all of these again in class today because it's all there in your notes. You just wanted to refresh how to count those domains to find your shape. Then we also refreshed bond polarity. So remember, electronegativity is how strongly an atom can attract electrons towards it. The only time we're really counting a bond as nonpolar in our class is if it's the same element. So if it's 2 oxygens bonded together or 2 chlorines, if I compare their electronegativity differences, we would say those are nonpolar. There's no difference. But to make things really simple for us this year, since we're all virtual and to cut down on the amount of work that we need to give you, we're saying that anytime it's 2 different elements, we're calling it a polar bond. Now, in actuality, carbon and hydrogen, the difference between their electronegativities is so small, that's actually considered nonpolar. But for us in class, we're just going to go ahead and say it is polar because it's different elements. We're not having you solve for polarity. So therefore, if it's different elements, we're automatically calling it polar. So if we know whether or not our bonds are polar, now we can look at the overall shape. So something is nonpolar if it has those polar bonds, but they cancel each other out. So here I've got carbon dioxide. I have some electronegativity difference between carbon and oxygen, but my domains are always equal and opposite. So whatever this difference is between carbon and oxygen, I have the same difference in a completely opposite direction. So I'm being pulled the same amount in 2 opposite directions. This makes it nonpolar. I don't get pulled to the left or to the right. No one is going to win this tug of war game. But over here, it's kind of like a 4-person tug of war. I've got 4 domains, but 2 of the people, those lone pairs of electrons, aren't really trying. So there's going to be a winner here. They don't cancel out. Someone wins, so this makes it a polar compound. So anytime that there's a lone pair, it's like one of the people in the tug of war game isn't really trying. They're accepting that they're going to lose, so there is going to be a winner. So lone pairs always make your molecule polar. So then I also gave you this flowchart. So the first question is, are the elements different? Now the answer is almost always yes. We very rarely give you compounds that are all the same element. So O3 is all the same, it's 3 oxygens, N2 is the same, it's 2 nitrogens. If it's all the same element, then your compound is nonpolar. But we usually give you at least 2 different elements in a compound. So if there's more than one element in the compound, is your molecule symmetrical? So linear, trigonal planar, tetrahedral can be symmetrical. Bent 120, bent 109.5, and trigonal pyramidal can never be symmetrical because they have those lone pairs. If you do have a potentially symmetrical shape, you need to look at your compound. So here, CH4 is symmetrical, it is nonpolar. I have equal and opposite domains, and I have the same difference of electronegativity on all sides. So this is going to be nonpolar. But if I have something like this, CH2F2, well, it is tetrahedral, it can be symmetrical. And looking at it as a Lewis dot structure, it looks pretty symmetrical. I've got hydrogens are opposite of hydrogens, fluorines are opposite of fluorines. It's not going to actually be symmetrical. I will always have a fluorine side and a hydrogen side. So if I have different elements, more than one kind of element hanging off my central atom, that makes it a polar shape. It makes it not symmetrical. After that review, we were ready to move on to the gizmo. Now, this gizmo is all about polarity of bonds, polarity of molecules, and then it goes into our next topic, which is intermolecular forces. So when you go to the gizmo, if you see this, the free gizmo full access with an account, it means you're not logged in, and it's going to give you a 5-minute countdown to work with this gizmo. That's not enough time to finish this assignment. So you need to make sure that you are logged in with your account. If you've forgotten your username and password, send me an email. I can look it up for you. So in all of our classes, we got to slightly different parts of the gizmo. I will, however, go over that first page because we did all get that first page done as a class. So first it asks about tug of war between a small child and a big bully. Well, if they're having a tug of war, that ball in the middle of the rope is going to go towards the bully. He's stronger. He's going to pull harder. But if you have the same person or two people with equal strength, that ball's not going to go towards either side. It's going to be a stalemate. No one is going to win that tug of war game. Then we started looking at the simulation itself. We started looking at sodium and chloride. So I'm going to take the sodium and the chloride and ask, what do we notice changes when I have it bond? So I'm going to press the play button. There's quite a few things that we can see happens here. I have a big sodium and a little chloride. They're both purple. When I press play, now my sodium is smaller, my chlorine is larger. They went from purple, they both started purple. My sodium is now blue, my chloride is now red. And I can see that that has a charge. It has a +1 charge on my sodium now and a -1 charge on my chloride. So these are 3 things we notice that change when I make them bond. Then the gizmo asks about who has those electrons from the sodium. So we can see that those electrons left the sodium and came to the chloride. We can tell that this happened 2 different ways. First off, my chlorine has a negative charge. It went from neutral to negative. That means it's gained an electron. Remember, electrons are like homework. The more you have, the more negative you feel. Chlorine went from being neutral, so a normal amount of homework, to suddenly being negative, so suddenly having twice as much homework as expected. So my chlorine seems to have gained that electron just based on its charge. Now, another thing you could point out, though, is its size. Its size got larger. Remember when we were talking about effective nuclear charge? Well, that same effective nuclear charge is still being felt by that valence shell of electrons, but now it's being shared by more valence electrons, so they actually expand out. Then it asks what happens to the colors. So they both started as purple. Then my sodium turned to blue and my chloride turned to red. So what happened is that their charges changed. Changing from purple to blue means you've gained a positive charge, whereas going from purple to red means you've gained a negative charge. Now remember, these gizmos are designed for you to follow those instructions and comment on what you see. When it's telling you to sort things, it'll tell you if you're correct or incorrect. So my next thing tells me to take it and put it into ionic bonds, which is correct. Remember, metal and non-metal makes an ionic compound. If you sort things incorrectly, it'll tell you, and you can correct yourself to make sure that your answers are correct in the gizmo. So remember, finishing that gizmo is your homework due Thursday or Friday, whichever day is your class. I'm available all Wednesday. You don't have to wait until your scheduled class period to come in and see me on Wednesdays if you need any help or if you just want to hang out, just want to talk. I'm there all Wednesday. Please come by and visit. So I hope everyone has a wonderful week, has a wonderful start to 2021. And until I see you guys again, everyone stay safe and make good choices.